Alright, so this is the honors chemistry version of the section 16.3 lesson video. Remember, if you want an easy way to get all my videos at the same time for the whole year, you can just subscribe and they'll all come up. So this is about colligative properties. So a property that depends upon only the number of solute particles, not the type, is called a colligative property. So like we don't care if we're dissolving sodium chloride or calcium chloride or lithium oxide. It doesn't matter what we're dissolving into the solvent, we care how much is in there, how many particles. So we're going to have to be careful with ions there. So four colligative properties that we're going to talk about are vapor pressure depression, freezing point depression, boiling point elevation, and then we're going to talk about osmosis just a little bit. I cover osmosis a little bit more in AP, but I will at least introduce it here. So of course, depression means it goes down, so vapor pressure is decreasing, freezing point is decreasing, and boiling point is elevating or going up. So the important thing to remember is that when something dissolves in a solvent, and so for simplicity reasons, I'm going to say something dissolving in water for today, just so that's easier than, consistently referring to it as solute and solvent and getting confusing. When something dissolves in water, like an ionic compound like salt, NaCl, remember how we talked about the water molecules will surround the ions to where the hydrogens, which are more partially positive, are attracted to the negative ions, and the oxygens, which are partially negative, are attracted to the positive ions. So the thing you have to remember for colligative properties is the solvent or the water, they really, really, really like the ions. The ions are something new and attractive, and so they want to surround them. It's kind of like if a famous person shows up to your school. Everybody wants to surround them and get their phone out and take pictures and everything. They're not just going to keep hanging out with each other. The kids at school see each other all the time. So if a celebrity comes in, they want to surround them. So think of it like that. The water molecules are everybody at your school, and the ions are these famous celebrities. And so again, they're very attracted to them. If you'll remember that, then all the colligative properties make total sense. So let's talk about vapor pressure depression real quick. So we've talked about vapor pressure in class. So vapor pressure is the pressure of a vapor above a liquid. So remember, it's about the molecules of a liquid evaporating and causing a pressure above the liquid. So the more particles that evaporate, the higher the vapor pressure. But to evaporate, that means the particles have to leave the liquid. Okay, so that's the thing you got to remember for vapor pressure. So the vapor pressure decreases when solute particles are added, because the solvent particles are attracted to the solute particles, so they do not want to leave the solution to become a vapor. So like I said, let's just focus on salt and water. So this is water by itself. These are all the kids at school. They see each other all the time. They're sick of each other. So some of them evaporate and become a gas, and they cause a little vapor pressure up here. But remember, the salt, ions from the salt, the sodium and the chloride, those are like famous celebrities. So when you add salt to it and it breaks into those ions, remember all the water molecules want to surround those ions because they're new, interesting, they're attracted to them. And so if you look, less of them will evaporate because they're so interested in surrounding those ions. So if you look between the two pictures, this would have a lower vapor pressure because less particles have evaporated to become a gas and cause a pressure. See, more particles have evaporated over here. So remember, think of those ions or that solute as a celebrity. The water molecules or the solvent is really attracted to those celebrity particles. So it doesn't want to leave and become a gas and go be by itself. All right, so that's vapor pressure. Let's look at freezing point. And the good thing about these is the explanation for all of them is the same. Okay, it's all about those solvent particles being attracted to the solute particles. So when a substance freezes, the particles must get in an orderly arrangement to form the solid. So think about ice. We've talked about that in class. It forms that honeycomb shape with the six-membered rings so that it can form the most hydrogen bonding possible. Remember, which is not a bond, it's an intermolecular force. So the freezing point lowers because when a solute is added, the solvent particles are attracted to the solute. So they don't want to get in that orderly arrangement. So that's the thing is, if you add salt, the water molecules are busy surrounding those ions. Remember, they're attractive, they're famous. They want to be around them. They don't want to get in an orderly honeycomb shape arrangement and form hydrogen bonding with each other. They could do that anytime. So what you have to do is you have to make it even colder to force them to get into the honeycomb shape arrangement. Because they're going to form a solid at some point. It just might be below 0 degrees Celsius, which is its normal freezing point. All right, and so boiling point, works the same way. We're just going in the other direction. We're going up. So the boiling point increases because when a solute is added, the solvent particles are attracted to the solute again. So they do not want to leave the solution and become a gas. So this is actually the same explanation as vapor pressure. So again, if we try to boil it, we're trying to make those water molecules leave and become a gas. Well, then they can't be with those attractive solute particles, those famous celebrity solute particles. Why would they want to leave and become a gas when they could surround those awesome particles? So what we have to do is we have to heat it up even higher to force it to boil. So that's why you add salt to water when you're cooking. It's also for flavor, of course. But like when you're trying to cook pasta, if you add salt to the water, then that increases the boiling point, so your pasta will cook a little bit faster. Like I said, it's also for taste, but you know, scientifically speaking, it's for increasing the boiling point. Alright, so last thing we got to talk about before we look at how some questions will be worded for this is we're just going to talk about osmosis just a little bit. There's a whole formula that you can use to calculate it and all that kind of stuff, and I will do that in my AP videos, but for honors, we're just going to kind of touch on what it is. So materials that only allow some molecules to pass through are called semi-permeable. So impermeable means nothing can pass through. So semi-permeable means some things can pass through. So for example, a membrane may allow small water molecules to pass through, but if it has like a larger solute dissolved in it, those particles won't be able to pass through. So what does it look like and what is osmosis? So osmosis is the net movement of solvent towards the solution with the higher solute concentration. Okay, it's kind of like when we talked about diffusion and effusion. It spreads out until they're equal. Well, if you have a semi-permeable membrane right here, it's hard to see in the picture, but there is one right here and right here. And when you start, if you look, this side has a higher concentration. You can see more red dots. So this is a high concentration, and this is low. So just like diffusion and effusion, we want to go from high to low concentration if we're spreading out a gas. Well, in this case, the solute particles can't pass through. So that's normally what should happen, is the solute particles should go to the side with the lower until they spread out. But remember, we said in this semi-permeable membrane, the solute particles can't pass through. So somebody has to make it equal. So what happens is some of the water will pass through. Because then if you look, see how now this side is much higher than this? They started out equally. This side's much higher, but now the concentrations would be the same. Now I know you're probably thinking, well, there's still more red dots on this side than on this side. Yes, there are, but the concentration, the molarity, because remember, molarity is moles of solute per liter of solution. Well, we have the same number of moles of solute, but now we have more solution. And so that's what equalizes those two concentrations. All right, you probably talked about osmosis some in biology too, when y'all talked about cell membranes and things like that. All right, so what are questions going to look like about colligative properties? Well, it's going to go back to ions and breaking them apart, which we've been doing since chapter 11, but some of you still have trouble with it. So remember, the colligative properties are based on the number of solute particles, not the type. So we don't care if it's a calcium ion, a chloride ion, a sodium ion, it doesn't matter. The solute particles could be atoms, ions, or molecules, so that's where you have to be careful. You must remember that ionic compounds will break into ions when dissolved in water. So for example, if I have CaCl2, a lot of y'all want to think that's one particle. But when that dissolves, you're going to get a calcium with a +2 charge, and you're going to get 2 Cls with a -1 charge. So you're going to get a calcium ion and 2 chloride ions, which actually makes 3 particles when it dissolves. So you have to be careful. If you see a metal and a non-metal, or a polyatomic ion, that means it's ionic and it's going to split up. So we got to keep that in consideration. So let's look at a question. So it says, which solution has the higher boiling point? Well, remember, one of our colligative properties is boiling point elevation. And so what that means is the more particles I have, the higher the boiling point. Okay, so in other words, I need to pick the one with the most particles. The reason I specify that is you're not always picking the one with the most particles. You got to be careful. All right, so it says I have 3 moles of magnesium sulfate and 1 mole of aluminum oxide. So you may be real quick to decide, okay, well this is 3 moles, this is only 1, this is going to have more. But remember, you have to take into account it breaking into ions. So this is ionic. It is a polyatomic ion is in this. It's a metal with nonmetals. So when it breaks up, you're going to get Mg with the 2+ and SO4 with the 2- charge. So you really get 2 particles. So 3 moles times 2 particles each, of course, makes 6 moles. Now, are y'all going to write all this out? Probably not. You'll probably do most of this in your mind. Okay, so we get 2 particles when it breaks apart 2 ions, so we multiply by how many moles we have. So I get 6 moles of particles with the first one. For the second one, we have a metal and a non-metal, so I know it's going to split up. So I'm going to get 2 aluminums with a +3 charge and 3 oxygens with a -2 charge. So I'm actually going to get 5 particles here. So I do my 1 mole times my 5 particles. And so I get 5 moles of particles total. So who has more particles? Well, it does end up being solution A. But remember, if you picked it just because solution A seemed to be bigger in the beginning, it's not always going to work out that way. Okay, so you got to be really careful of that, because sometimes it will work out that way, where the one you thought was bigger really is, but sometimes it's not. So always check first. All right, so let's erase, and I will let you try a couple. Alright, so it says which solution, oh sorry, you try these first on your own real quick, and then of course pause, try them, and I will go over. So which solution has the lower freezing point? Well, freezing point depression is our colligative property, so it does get lower with more particles. So I'm again going to pick the one with the most particles. So right now it appears to be solution A, but we're going to have to check to see. Alright, so nitrogen and oxygen, that is 2 nonmetals. If it's 2 nonmetals, it is a molecule. Remember, molecule is M/C. It is a molecule. A molecule does not break apart. So we're just going to get 1 particle. That's the important thing to remember. If you try to break it up into 2 N's and 5 O's, you're going to get the wrong answer. So I have 3 moles of particles in solution A. So remember, if it's 2 nonmetals or more nonmetals, it's molecular and it's all going to stay together as one thing. All right, solution B, on the other hand, I see polyatomic ions. I know it's going to be ionic. So instead of writing them all out, I'm clearly going to get 1 calcium and then 2 nitrates, which gives me 3 particles. Okay, 1 calcium and then 2 nitrates. So that's 2 moles times 3 particles. And so I end up getting 6 moles of particles. So see, in this one, it ended up being solution B, even though in the beginning it seemed like it should have been solution A. All right, so hopefully you got that one right. That's the tricky part, is that molecular compound. Okay, if it's only nonmetals, it's not going to break apart. So just maybe make yourself a note of that. All right, so then it says, which solution has the higher vapor pressure? This one had another trick, because our colligative property is vapor pressure depression. That means it gets lower. So instead of picking the one with the most particles, I actually want the one with the least particles. Okay, so if I ask you the colligative property the way it is, like freezing point depression, I ask you lower, you always pick the most particles. But if I ask you the opposite...
Mr. Tyler, you're needed in the front hallway. Your guests are arriving. Mr. Tyler, to the front hallway, please. Your guests are arriving.
Well, there we go. Alright, so if I ask you the opposite, like it's vapor pressure depression, which means lower, but I ask you for higher, you do the least amount of particles. Okay, now this one, in the beginning, it's going to seem like they're the same, because it's 1 mole of each, but we know better than that now. Alright, so I see polyatomic ions, so this is going to break apart into 2 particles, ammonium and nitrate. So I do my 1 mole times my 2 particles, and I get 2 moles. So solution A has 2 moles total. Here I have a metal and a nonmetal, so I'm going to get 1 aluminum and 3 bromine or bromide ions. So I'm going to get 4 particles here. So 1 mole times 4 particles gives me 4 moles. So normally you would select solution B because it has the most particles. But since I asked you the opposite of the colligative property, we want the one with the least particles, which ends up being solution A. So hopefully my 2 little tricks about giving you the molecular compound and asking you higher vapor pressure did not throw you off too bad. And if it did, then just don't make the same mistake again. Alright, so let's move on because we're almost done. Alright, so what are 3 colligative properties? Well, remember we said there is vapor pressure depression, freezing point depression, and boiling point elevation. Okay, so I just do VP for vapor pressure and an arrow down for depression like that. So vapor pressure depression, freezing point depression, boiling point elevation. What factor determines how much the vapor pressure, freezing point, and boiling point of a solution differ from those properties of the pure solvent? So in other words, what it's asking is, what determines how much lower vapor pressure is or how much higher boiling point is? Well, remember, it's not the type of particles, it's the number. The number of solute particles. And then I would just maybe put in parentheses next to that, not the type. Like, we don't care what they are, we just care how many we have. So the number, not the type. And then it says, would a dilute or a concentrated sodium fluoride solution have a higher boiling point? Well, remember, boiling point elevation is our colligative property. So that means the boiling point is higher with more particles. So in other words, would a dilute or concentrated sodium fluoride solution have more particles? Well, dilute means a small amount of solute, and concentrated means a large amount of solute. So who would have the higher boiling point? It would be the concentrated sodium fluoride. Well, here, I'll just circle concentrated. Concentrated sodium fluoride solution. The reasoning is because concentrated means a large amount of solute. And the more particles, the higher the boiling point. Okay, so our explanation is already there. Alright, so let's move on to our last slide and let's look at some of those colligative properties again. So it says, an equal number of moles of Ki and MgI2 are dissolved in equal volumes of water. Which solution has the higher, and then we have boiling point, vapor pressure, freezing point. Alright, well first let's determine particles. So Ki, that's a metal and a non-metal. So I'm going to get 2 particles every time Ki breaks up. Now since they didn't give me a mole amount, then I don't need to multiply by anything. And then MgI2, that is also ionic because it's a metal and a non-metal, but I'm going to get 1 Mg and 2 I's. So I'm actually going to get 3 particles. So then it says, which one has the higher boiling point? Well, our colligative property is boiling point elevation, so that means I want the one with more particles. So who has more particles? The MgI2. So that one would have the higher boiling point. Well, then it says, which one has the higher vapor pressure? Well, my colligative property is vapor pressure depression. So I don't want the one with more particles, I want the one with less particles. Because remember, if it's the opposite of the colligative property, we want less particles. So who has less particles? Ki. And then last one says, which one has the higher freezing point? Well, remember, freezing point is also depression, so it's going to go down. So again, since I want higher, I'm going to look for less particles. And that again is Ki. Okay, so you just have to be real careful about making sure to break up ionic compounds, leave molecular compounds together, and then just make sure you look at, am I asking you about the colligative property or the opposite of the colligative property? If I'm asking you the colligative property, you look for more particles. If I ask you the opposite, you look for less particles. All right, and that is section 16.3. Hopefully it was helpful for you.